All right, guys. So we've diphosphorylated our initial glucose molecule. I summarized it down to the point that we have this relatively symmetric fructose 1,6-bisphosphate, 6-carbon sugar in a furanose 5-membered ring with phosphates on the 1 carbon and on the 6 carbon, right? So here's our 1 and again, and here's our 6, right? Okay. Now, what we need to do is the real business end of this pathway in some ways, the actual splitting reaction. That happens right here at reaction 4, right? Where we're gonna now take the glucose, right? And we're gonna basically split, right? So here again, here's 1, 2, 3, 4, 5. We're now gonna split that bond, right? Between carbon 3 and 4. And we're gonna do that to generate these 2 3-carbon halves of this molecule, one of which is a ketone, and one of which is an aldehyde. So the ketone looks like this, right? One of the methyl groups has that phosphate group on it. Oh, sorry. Right? This is, of course, dihydroxy acetone phosphate, or DHAP. The other half of the molecule is an aldehyde, of course, that looks like this. Right? Right. This, of course, is glyceraldehyde 3-phosphate. Or GAP. Right? The enzyme that runs this reaction is known as aldolase, because it's essentially running what is the inverse of an aldol condensation. And the free energy change for this reaction, this will bend your noodle a little bit. The standard state free energy change, let me move this over a little bit, it's a little sloppy here. The standard state free energy change for the aldolase reaction is plus 23.9 kilojoules per mole. Okay, now I said sit and let the PGI free energy, standard state free energy, sink in for a second. Let that one sink in for a second. That's an order of magnitude less favorable than the unfavorable PGI reaction in the forward, the glycolytic direction. Aldolase really doesn't, I mean, energetically, fructose 1,6-bisphosphate really does not want to decay into these 2 3-carbon sugars, right? Which I'm hopefully you're going to recognize, with the exception of that phosphate group, right? Here and here, those are the 2 trioses we started out with, right? Dihydroxyacetone and glyceraldehyde, right? Now they're just phosphorylated, right? So maybe you can sort of see where we're going with this in a second, right? Okay. What do we do? I mean, with a free energy that unfavorable, how on earth do you ever get this reaction to go? Well, after talking about the PGI reaction, you probably have some rough idea of what's going on here. The concentration of GAP and DHAP, right, in a living cell are kept so low, right? You talk about draining that other pool. Boy, does the DHAP and the GAP concentration have to be kept so low that it becomes possible to pull that free energy in the forward direction if you want to run glycolytically, which means almost as soon as DHAP and GAP get made, they get utilized in the next subsequent steps in order for this pathway to run, because that is a big free energy barrier to overcome. But amazingly enough, if the subsequent part of the pathway is aggressive enough in draining those pools, you can do it. And it turns out the free energy change for this reaction under cellular conditions with the DHAP and GAP pool being drained and the equilibrium being pulled to the right is actually minus 1.3 kilojoules per mole, right? So it's absolutely possible to take a reaction that is that unfavorable at standard state and pull it in the forward direction, right? Okay, so now here's the question. How do you get this reaction to go, right? We need to split that 3,4 bond, which means we got to pull the electrons out of that bond and we've got to make them go somewhere, right? Where are they going to go, right? Well, in principle, maybe you have this guy here. That's a carbonyl carbon. That's electrophilic, right? Maybe we could take the electrons and shove them over into that carbonyl. Except we're going to have to open the ring first. Number one. Even then, let's look at this in a little more detail, right? All right, so let's think about that aldolase reaction. Here's the ring open, right? We've opened that ketose sugar. There's the carbonyl group right there on carbon 2, right? And remember, here's the bond we need to split, that 3,4 bond. So you could imagine, well, I could shove these over here maybe, and these could go up here, right, to make sort of a oxyanion, right? But you know, if that was that spontaneously favorable, fructose 1,6-bisphosphate would fall apart by itself all the time, right? Which basically doesn't happen. Tells you then how unfavorable the free energy of that transition state turns out to be. So we need to create a better electrophilic sink. And we've got a carbonyl. Think back to my discussion about covalent catalysis. How might you do that? Maybe you'll remember that if you replace that carbonyl, or you activate it with a primary amine to form a Schiff's base, yeah, you've got a possibility for doing that. And it turns out aldolase is a key active site lysine residue that does exactly that, right? This active site lysine will replace the oxygen to form a Schiff's base. And the other thing, if you remember, we need to do to split that bond is we need to basically, we're going to turn the second half, right? This half of the molecule, right? We're going to turn that into an aldehyde, which means we need to basically pull that alcohol proton off here and make those electrons form that aldehyde. Okay, well, even if we've made a good electrophilic sink up here, we need to help drive that, and aldolase has in the active site a strategically placed base that's ideal for helping abstract that proton, helping provide an opportunity now for those electrons to flow into forming that aldehyde carbonyl, which now, because we have this nice electrophilic sink over here in the Schiff's base, can take up the electrons as this 3,4 carbon-carbon bond splits, right? You do that, we now kick off the glyceraldehyde 3-phosphate, the GAP, there goes the aldehyde, but the ketone is still stuck to the enzyme, right? Okay, well, we just reverse this. We got that base now turns into a conjugate acid, right? And we can just put that proton right back onto that carbon to now generate the Schiff's base analog of that ketone, right? What's going to become dihydroxyacetone phosphate. All we got to do now is put in a little water. We've regenerated the enzyme and we've made our dihydroxyacetone phosphate, right? Pretty cool, pretty straightforward. Hopefully the chemical logic of that makes some sense, right? Okay, fine. Let's come back over to where we were here, reaction 4. We've made glyceraldehyde 3-phosphate and DHAP, right? And what you may or may not remember, glyceraldehyde 3-phosphate is the thing we really need. That's what's going to go down the rest of this pathway. DHAP directly is not useful. That ketone is not useful for creating energy. It can be used, it's used in lipid biosynthesis, glycerol biosynthesis, but it's not useful for making energy. So did we just like only get a 50% yield? Remember back to my discussion about these saccharides, monosaccharides. Remember the relationship between a ketose, right, and an aldose? They can be interconverted. Just like we did with PGI, DHAP and GAP are tautomers of each other. So it turns out the simple solution here, and the reason the chemistry works the way it does, is that we can take one half of this guy, and in reaction 5, turn that more or less not immediately useful dihydroxyacetone phosphate into glyceraldehyde 3-phosphate, right? So again, here's our not so useful, not as useful DHAP. Right, there's the phosphate group. And what this enzyme is going to do, the next reaction is going to do, is basically just convert that molecule from the ketose into the aldose. We're just going to take the carbonyl, move it over, right, and turn DHAP into GAP, right? The enzyme that runs this reaction, it's a famous one. This is, of course, triose. Oops. Phosphate isomerase, or TIM. Mighty Tim for you Monty Python fans, right? The free energy balance for this reaction, the delta G naught prime for the TIM reaction, not so awesome. Is plus 7.6 kilojoules per mole, right? And I actually don't have on me the cellular condition, the actual free energy change under typical cellular conditions. It may not, could be it hasn't been measured, or I just don't have it in my notes, but it's favorable, right? The delta G prime is going to be less than 0. It's negative, right? So we've got another reaction here. So this tells you, from the thinking about the aldolase reaction, I said these concentrations have to be low, but what ultimately really has to be flowing downhill in a really big way, right, is GAP, right? Because the depletion of GAP is going to both pull the aldolase reaction as well as the triose phosphate isomerase reaction in the direction of GAP. As you deplete this guy, as you deplete GAP, as you pull this guy downhill, right, you keep that concentration not super low as it flows into the rest of this pathway. You're going to pull both preceding steps, the aldolase reaction and the triose phosphate isomerase reaction. Okay, so you've seen several examples of reactions that standard state are unfavorable, and that the concentration balance of reactant and product is tipped in such a way by pulling the equilibrium, by depleting the reactants and shifting the equilibrium in the forward direction, right? That's going to become important later on when we talk about how this pathway is used in a slightly different way, right? Okay, let's look at TIM a little bit, because I mentioned it before, and we can come back to thinking about some things about enzymes, right? So remember, triose phosphate isomerase is one of these canonical enzymes in terms of its structure, right? TIM is built around this barrel-shaped structure, this rosette-like structure of these parallel core beta barrel made from parallel beta sheets that are flanked then by these buttressing alpha helices. Makes this sort of beautiful little like Danish kind of structure. And evolution hit on this structure as an awesome way to build enzyme active sites, because there's this great pocket in the middle of this beta barrel that's used over and over and over and over again. It's often called a TIM barrel because the first enzyme where this was recognized as a motif structurally was this enzyme, triose phosphate isomerase. So you'll hear when people refer to TIM barrels, this is what they mean and this is why, right? And there are several key residues in the active site, right? But there's a couple of really important ones. There's this glutamate and this histidine, because remember, ultimately the reaction we're going to run here is a tautomerization reaction, right? Just like we did with PGI. Now I'm going to show it to you explicitly, a little like 1-2 punch of acid-base catalysis to get this tautomerization reaction to run, right? So in the active site of the enzyme, here's our DHAP, right? There's the ketone. There's that sort of #1 carbon relative to ketone, that sort of alpha to the the carbonyl group that we want to turn into an aldehyde, right? So we have a little, like I said, 1-2 punch. We need to protonate that carbonyl group. At the same time, the glutamate is going to act like a base, which you don't normally think about glutamates doing, right? To take up that proton off that methylene carbon. Now you could look at that and go, right? How's the pK of that guy ever strong enough to abstract that proton, right? And this is a similar sort of issue that we talked about serine proteases, right? Well, that proton is already acidic, right? Because it's compared to a normal methylene or methyl carbon because it's alpha to that carbonyl group. And there have to be features of the active site, including the fact that this histidine is going to act as an acid to protonate the sort of nascent alcohol group forming on that carbonyl and other features of the active site that make this a favorable reaction, right? So that little 1-2 punch, acid base, helps pop off that proton, protonate the carbonyl to form what we saw when we talked about carbohydrates earlier, that enediol intermediate, right? There's the carbon-carbon double bond and then the 2 alcohol groups. Now all you have to do is reverse it, but make sure, or hope this happens, on the end of the molecule where you want to put the aldehyde. So now in this case, the histidine will act as an acid to pull the proton off the 2 carbon, as a base to take the proton off the 2 carbon. The glutamate is now going to act like an acid and donate a proton over here to that same 2 carbon, cross that double bond to regenerate now at that alcohol group. And we've now moved the carbonyl over to form an aldehyde, right? Okay. Now, great, fairly straightforward, sort of simple acid-base chemistry, 1-2 punch, right? Now, there's an interesting feature of this reaction that's worth thinking about. And that's that if you, well, there are a couple interesting features about it. One, this enzyme, triose phosphate isomerase, has a kcat over Km of approximately 10 to the 8th per molar per second. So what does that mean? And how do you think maybe that helps explain some of what's going on here in terms of pulling this pathway in the direction we want, right? You think back to our discussion about kcat over Km, that means triose phosphate isomerase, right, has achieved something close to catalytic perfection. This molecule, essentially, once it engages a substrate molecule, it doesn't really ever let go, right, until there's a product in the active site. Okay, so that's really good, right? Number one. There's another interesting wrinkle to this reaction, which is that if you think about this, what we're going to be doing here is we're going to be taking this ketone, DHAP, right? All right, and we're going to form that enediol intermediate, right, which would be something like this guy. Right, and what we want to do is we want to move what was a carbonyl here in this ketone, we want to move it down here, right, to form that aldehyde. But it turns out if you form this enediol intermediate in free solution, there's a side reaction that progresses, 100 times faster than the formation of GAP, right? And it creates this molecule known, it's this dicarbonyl molecule known as methyl glyoxal. Right? And methyl glyoxal is dead end, right? There's no getting that molecule back. You can't really do anything with it. You've wasted basically a GAP equivalent, right? This happens in free solution. And you can sort of imagine why, if you wanted to pull that proton off, right, and get the electrons here to flow back down to form that aldehyde, these guys are going to come up here. If you don't have a proton sitting here waiting, right, in the active site of the enzyme, it's just as easy to reform a carbonyl here, all right, kick that proton off, and you've made methylglyoxal. That's bad. That's what you don't want to have happen. Well, TIM, the enzyme, has in its active site, and you sort of may be visible, you see this set of residues here, that loop, right? When there's substrate in the active site, this loop closes over the top of the DHAP, right? And the loop, if there is the enediol intermediate is in the active site, that loop won't open, right? The loop will only release when either, or the dynamics of the loop are such that it is bound so tightly to the enediol intermediate that the enediol can't escape. And it only then becomes flexible when there's either DHAP or gap in the active site of the enzyme. So again, you see another example where the enzyme dynamics are designed to prevent a side reaction that would otherwise go in free solution at a very high rate and sort of kill the pathway. And the dynamics of the enzyme have evolved to recognize and eliminate the possibility of that side reaction, which is pretty neat. Okay.